Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
The 1998 Nobel lecture by Yoichiro Nambu, titled Dynamical Symmetry Breaking in Particle Physics, serves as a capstone intellectual autobiography, a carefully curated narrative tracing a revolutionary idea from its conception in one field of physics to its foundational role in another. This essay undertakes a profound evaluation of the specific claims, arguments, and conceptual frameworks presented within that lecture. It proceeds by analyzing a work section by section, assessing the internal logic, the methodological assertions, and the retrospective framing Nambu employs to articulate the journey of his seminal contribution. The analysis delves into the substance of Nambu's scientific reasoning as he presents it in 1998, examining how he constructs the intellectual lineage from condensed matter physics to the Standard Model, placing his own work as the critical, conceptual bridge. The purpose is to move beyond mere summary and engage directly with the lecture as a primary text, evaluating its arguments with the same rigor expected of its intended professional audience. Section 1: Nambu's Introduction and the Primacy of Symmetry. Nambu commences his lecture by establishing symmetry as the central, guiding principle of 20th century physics, a claim that functions as the intellectual bedrock for all subsequent arguments. He presents the progression from the spacetime symmetries of relativity to the internal, abstract symmetries of quantum field theory as a natural and aesthetically driven evolution. His evaluation of this history is explicit. These symmetries are beautiful, powerful, and predictive. The core claim of this introductory section is that the most profound insights arise when a symmetry, expected to be perfect, is found to be broken. He introduces two modes of this breaking: explicit breaking, where the underlying laws themselves contain a small asymmetric term, and spontaneous or dynamical breaking, where the laws are perfectly symmetric but the ground state, the vacuum, is asymmetric. Nambu's argument here is one of conceptual hierarchy. He elevates spontaneous breaking as a far more subtle and fruitful phenomenon. He claims that his unique contribution was the recognition of its dynamical origins, drawing an analogy from a completely different domain of physics. This framing is a masterful piece of intellectual stage setting. He presents the problem of particle masses, particularly the puzzle of the light pylon and the massive nucleon, as a prime candidate for a solution rooted in a hidden, spontaneously broken symmetry. The evaluation of this initial claim must acknowledge its rhetorical power. He positions his work as the resolution to a deep paradox that could only be understood by importing a radical new concept. The specific argument is that the physics of the strong interaction possessed a hidden approximate symmetry, now known as chiral symmetry, that the vacuum state failed to exhibit. This symmetry, leading directly to the observed particle spectrum. Section 2. The Bardeen-Cooper-Schrieffer theory as a template. The second section of the lecture makes its most crucial analogical claim that the Bardeen-Cooper-Schrieffer theory of superconductivity provided the direct mathematical and conceptual template for understanding symmetry breaking in particle physics. Nambu's evaluation of the BCS theory focuses entirely on its symmetry-breaking aspects. He argues that the key insight from BCS was the formation of a condensate of Cooper pairs in the ground state. This condensate, a macroscopic quantum phenomenon, represents a ground state that lacks the full gauge invariance of the underlying laws of electromagnetism. The U1, or circle group, symmetry of electromagnetism is spontaneously broken. He then explains the physical consequence: the emergence of an energy gap, a minimum energy required to create an excitation above this ground state. In his telling, this was the complete blueprint. The claim is direct: the mechanism by which electrons in a metal organize into a symmetry-violating ground state, thereby altering the excitation spectrum, could be transposed to the relativistic quantum vacuum. A critical evaluation of this claim reveals its brilliance and its boldness. Nambu asserts that the mathematical formalism, specifically the gap equation formulated by Bogoliubov and Valitin. With the tool he lifted, he presents the superconductor's ground state as a vacuum teeming with paired electrons, and he proposes to view the particle physics vacuum in a similar light, filled with a condensate of fermion-antifermion pairs. The strength of his argument in the lecture rests on the clarity of the parallel. He minimizes the profound conceptual leap required to equate a low-energy electronic state in a crystal lattice with the fundamental vacuum of spacetime. His presentation is one of calm, logical extension, portraying the move as almost self-evident once the BCS structure was properly understood. This section's central claim is that a deep physical principle, once uncovered in one area, reveals universal truths, a powerful testament to the unity of physics. Section 3, Application to Particle Physics and the Nuclear Mass. This portion of the lecture presents a substantive core of Nambu's original 1960 work with Giovanni Giornalasinio. The central claim is that the mass of the nucleon, the proton and neutron, is a dynamical consequence of a spontaneously broken chiral symmetry. He begins by positing a world where the fundamental laws of the Strom interaction possess an exact SU2 left cross SU2 right chiral symmetry. In such a world, he argues, the nucleon would be strictly massless. This is a radical assertion, as the nucleon's mass constitutes the vast majority of the mass of ordinary matter. His argument proceeds by direct analogy to the BCS model. He replaces the electron with the nucleon field. He replaces the attractive force mediated by phonons in a superconductor with the Strom nuclear force itself. The result, he claims, is the formation of a nucleon-antinucleon condensate in the vacuum, represented by the fermion bilinear condensate psi bar psi. This condensate, like the Cooper pair condensate, breaks the underlying symmetry, in this case, the chiral symmetry. The lecture's argument is that the energy gap of the superconductor finds its particle physics analog in the dynamically generated mass of the nucleon. The nucleon becomes massive because of its interaction with this structured, symmetry-breaking vacuum. The evaluation of this claim is twofold. First, the logical structure is elegant and compelling. It provides a dynamical origin for mass, transforming it from a simple parameter in a Lagrangian to a calculable outcome of vacuum physics. Second, the evidence he presents for this in the lecture is tied to the second major consequence of the theory. The breaking of the continuous chiral symmetry necessitates, via his own reasoning that would become the Goldstone theorem, the existence of a massless particle. He identifies this particle with the pion. The pion's small but non-zero mass is then explained as a consequence of the chiral symmetry being only approximate in the first place, due to small but non-zero bare quark masses. This transforms a problem, the pion's anomalous lightness, into a key piece of evidence. The claim is thus a unified explanation for two seemingly disconnected facts: the large mass of the nucleon and the small mass of the pion. Section 4, the emergence of the Nambu-Goldstone boson. In this section, Nambu reflects on the general principle of what became known as the Nambu-Goldstone boson. His central claim is that the existence of a massless, spin-zero particle is an inescapable and general consequence of the spontaneous breaking of any continuous global symmetry. He presents his 1960 work as the first concrete physical model demonstrating this general theorem. He recounts how his model predicted a massless pseudoscalar meson before he identified it with the pion. His argument is that this massless mode is the collective excitation of the ground state condensate, the gentle, long-wavelength fluctuation of the new vacuum order. It is the physical manifestation of the broken symmetry itself. In his retrospective, Nambu subtly credits himself with deriving the result in a specific, physical context, while acknowledging Geoffrey Goldstone's role in later formalizing it into a more abstract and general mathematical proof. There is a touch of intellectual irony in his presentation. He explains that for many physicists at the time, the prediction of a new massless particle was seen as a fatal flaw in any such theory, as no such particle other than the photon was known. His claim is that he recognized the supposed flaw as the theory's greatest triumph, as it provided a perfect candidate for the mysterious peon. An evaluation of this section's argument must focus on its pedagogical clarity. Nambu explains the essence of the theorem without complex mathematics. He uses the analogy of a ferromagnet. The laws governing atomic spins are rotationally symmetric, but in the ground state, all spins align in a specific direction, breaking the symmetry. The Nambu-Goldstein boson is the analogue of the spin wave, a low-energy excitation that corresponds to slowly rotating the direction of magnetization. That claims power lies in its universality. It established a concrete, observable prediction for a very abstract concept, linking the structure of the vacuum to the particle spectrum. His lecture frames this discovery as the moment when spontaneous symmetry breaking matured from a curious mathematical possibility into a predictive physical principle. Section 5. Integration into the Standard Model and the Higgs question. Nambu then turns his attention to the Weinberg-Salam electroweak theory, the cornerstone of the Standard Model. His primary claim in this section is that the Standard Model's mechanism for generating the W and Z boson masses is a direct application of his principle of spontaneous symmetry breaking, albeit with a crucial modification. He explains that in the electroweak case, the broken symmetry is a local gauge symmetry, SU2 cross U1, rather than a global one. He correctly articulates the profound consequence discovered by others like Higgs, Brout, Inglet, Guralnik, Hagen, and Kibble when a local symmetry is spontaneously broken. The Wood-Nambu-Goldstein bosons are absorbed by the gauge fields, becoming their longitudinal polarization states and thereby giving them mass. The massless bosons disappear from the spectrum, solving the problem that had plagued earlier applications. In his narrative, Nambu presents this development as a vindication and a powerful extension of his original idea. However, he introduces a crucial point of critical evaluation concerning the Standard Model's specific implementation. He claims that the Standard Model achieves this breaking through the introduction of a fundamental, elementary scalar field, the Higgs field. He contrasts this with his original model, where the breaking was dynamical, caused by the condensation of existing fermions. Nambu's argument here is subtle and forward-looking. He presents the Standard Model Higgs mechanism as phenomenologically successful but conceptually incomplete. He poses the question of whether the Higgs boson is truly a fundamental particle or, in a deeper echo of his own work, a composite object, a bound state of some new, yet undiscovered fermions. This claim serves as a gentle critique of the Standard Model from the perspective of a dynamicist. He is evaluating the prevailing theory against his own aesthetic and physical preference for dynamical origins over postulated elementary fields. The strength of this claim, as presented in 1998, lies in its identification of the Higgs sector as the least understood and most weakly constrained part of the Standard Model. A prescient observation that continues to motivate a great deal of theoretical research. Section 6. Concluding remarks and future directions. In his concluding section, Nambu synthesizes the lecture's themes and speculates on the future. The central claim here is that the principle of dynamical symmetry breaking remains a vital and potentially more fundamental concept than the specific Higgs mechanism of the Standard Model. He champions this idea by highlighting theoretical frameworks that embody it. He explicitly mentions Technicolor, a class of theories where the electroweak symmetry is broken dynamically by a condensate of new fermions, called technifermions, bound by a new strong force. He also points to top quark condensate models where the very heavy top quark, discovered just a few years prior to his lecture, might itself form a condensate that breaks the electroweak symmetry, an idea he himself had explored. The argument he puts forth is that nature seems to prefer composite structures and dynamical solutions. He cites the progression from atoms to nuclei to nucleons, each level revealing a deeper layer of compositeness. His final claim is an extrapolation of this historical trend. It is natural to assume the Higgs sector of the Standard Model will also reveal a deeper, dynamical, composite structure. An evaluation of this concluding argument must see it as both a statement of personal scientific philosophy and a research program. In 1998, With a Large Hadron Collider on the horizon, these were vital, open questions. Nambu uses his Nobel platform to argue for a particular direction for future inquiry, one rooted in his own legacy. He champions a vision of physics where the fundamental entities are fewer and the observed complexity of the world, including the masses of its elementary particles, emerges dynamically from the complex structure of the vacuum. This final claim positions dynamical symmetry breaking as an enduring paradigm, a wellspring of ideas that will continue to shape the quest for a more complete understanding of nature's laws. In conclusion, Yoichiro Nambu's 1998 Nobel lecture is a document of immense intellectual weight, a retrospective that functions as a definitive statement of a physical principle. The evaluation of its internal claims reveals a masterfully constructed argument. Nambu methodically builds his case, starting with the abstract beauty of symmetry, importing a concrete mechanism from the physics of superconductivity, applying it to solve the long-standing puzzle of hadron masses, generalizing the result into a universal theorem, and finally, using it to frame and gently critique the very standard model it helped to create. Each section's claims are presented with an understated authority, where revolutionary leaps of imagination are portrayed as logical, almost conservative, extensions of established knowledge. He argues for the primacy of dynamics over postulation, for emergent complexity over fundamental complexity. The lecture's ultimate claim is that the vacuum is the central actor in the drama of particle physics, and that its hidden symmetries, and the manner of their breaking, dictate the very substance of the world. By evaluating the specific arguments he chose to present and the narrative he wove around them, we gain a unique insight into the mind of a physicist who taught his generation to see mass, and indeed the universe, in a profoundly new way. The lecture stands as a testament to the power of analogy, the unity of physical law, and the enduring quest for dynamical explanations at the heart of fundamental science.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.